All right, this will be the video lecture to accompany our discussion of discrete probability distributions. Our learning objectives and new content today are going to be to focus on turning word problems into probability statements, represent binary outcomes using a Bernoulli random variable, and calculate probabilities using the binomial distribution. To do this, we're going to discuss some new topics, one of which is a random variable. We're going to talk about some specific random variables, the discrete uniform random variable, the Bernoulli random variable, and the binomial random variable. We're then going to learn how to calculate probabilities using the binomial distribution in Excel using the binom.dist function with a variety of examples. And there are two flavors of this function, one which is going to provide us probabilities of observing an exact event. The other is going to provide us the probability of seeing some cumulative event in the distribution, and we're going to learn what those terms mean as well as how to rearrange other probability statements and fit them within the framework that Excel can use to provide us calculations. And as usual, nothing will be done in R today. Our lesson plan is going to walk just straight through these things. We're going to start with a basic on what I mean when we're talking about statistical modeling and what we're going to be doing for the rest of the class going forward here. We're going to introduce what uniform random variables are. We're really going to spend a very little amount of time on them. They work out as a nice introductory example, and I'm going to produce a computer simulation here for you shortly. And so there it's going to be useful to know what a uniform random variable is. Once we've done that, we're going to focus on the Bernoulli random variable and the binomial random variables. All right, so let's get started with our introduction to statistical modeling. All right, let's start with a simple example here that's going to help us motivate how we're going to think about statistical models. So let's suppose we wanted to project how a salesperson would do their first year on the job. We may hope to answer questions like, what are the chances she goes a whole day without making a sale? How many sales can I expect her to make on a typical day? And will she be successful enough to cover her salary? What we're going to do is figure out a series of statistical models that might be useful for answering these sorts of questions. In order to answer these questions, we're going to start working with statistical models. Now, a statistical model is just a mathematical representation of a real-world situation that helps us understand the likelihood or probability that we observe some particular outcome that we will refer to as an event out of all the possible things that could occur. And that set of things that could possibly occur is called a sample space. Now, there's always going to be a trade-off between how realistic and how quantifiable our statistical model is. The things we're going to focus on in this class will be pretty readily quantifiable, only requiring very simple calculations or functions that we can implement inside Excel. But to make sure we understand how reliable the predictions of those models are, we're going to outline the assumptions that these models require. And these are going to give us a feel for how realistic our predictions are. Now, in every situation, we're going to represent the object of our statistical model, whose outcome we have an interest in, with something called a random variable. Now, we're going to use this random variable, and we're going to use a placeholder, x or y, to represent the outcome we're interested in. Now, there are many different types of random variables, and we're going to get into a bunch in this class, but for today's lecture, we're going to focus on three specific types: the uniform, the Bernoulli, and the binomial random variable. And what these are a description of the way we calculate the probability of an event given the assumptions we're willing to make. So each one of these types of random variables will have different assumptions that go with it about the data, and we're going to identify the one that is appropriate for the problem we're trying to model. So before we get into identifying the assumptions that go behind these, let's think about some examples of what random variables are, what I mean by events, and what I mean by the sample space. So suppose we were going to model the outcome of a coin toss. Well, we could let x, our random variable, represent the outcome of that coin toss. We could denote the sample space, which is the set of possible things that could happen. And the way we're going to read this is that x is an element of the set. This little symbol here means an element of, and these curly brackets are telling us that they're the set of possible outcomes. X is an element of the set H or T. In English, this just says x can either be H or T. One possible event here is x is equal to h. Again, in words, we would say the coin landed heads. So we might be interested in understanding the outcome of this coin toss, and we might say, what is the probability of observing a head? This would be p of x equals h. Another possible random variable here, a very simple one, x could represent the outcome of rolling a dice. The sample space here, if we're looking at a traditional die, would be x is in the set of numbers 1, 2, 3, 4, 5, or 6, and one possible event is x is equal to. In words, we would say the die came up 2. We could think about something like whether or not a salesperson makes a sale. The sample space here is either yes or no, they make a sale or they don't make a sale. One possibility here, x equals no, would be the salesperson doesn't make a sale. Finally, we're going to introduce one other possible random variable x. It says x can represent the number of sales a salesperson makes in 10 attempts. The sample space here is 0, 1, all the way through 10. One possible event is x equals 4. In words, we would say the salesperson had 4 successful sales. Now, in terms of the content on the previous slide, we didn't actually have to state anything about probability. All we did was we defined a random variable, which was the object we were interested in modeling, and then described it in terms of an event and the set of possible things could occur. The reason we didn't focus really very much on probability is because we don't really know how to determine the probability of an event until we know what we can assume about the data. So when I say assume here, what we're going to try and do is identify the key characteristics of the data generating process, or the things that we think are driving the outcomes that we're interested in modeling. And once we've got those key elements, we're going to be able to identify relatively quickly what set of assumptions are consistent with those key elements. So let me give you an example here of what I mean. We're going to say x could be the outcome here of flipping a coin. What is p of x equals h? Okay, so this is an extension of our notation from the previous slide where we said x equals h is an event that the coin that we have flipped takes on the outcome h, which means the coin landed head. P of x equal h is just a way of saying what is the probability that the random variable x takes on the value h? What is the probability we observed a head? Well, this turns out to be a statement about, a pretty straightforward statement about probability, but it's going to depend on what we assume about the coin. If we have a fair coin, then this is a nice, easy example, then we know there's only 2 outcomes here. Each one is equally likely, and so the probability of a head is equal to the probability of a tail, which is equal to 1/2 each. If not, then we'd have to make some alternative model that would be a more reasonable way of predicting what these outcomes are. So this is all I mean by identifying the assumptions. As long as we have a reasonable way of outlining what the likelihood is of any one of these outcomes, we'll be able to calculate a probability very quickly. Once we've identified which random variable is appropriate, it's a really simple matter of just plugging those little pieces of information we're going to talk about here in just a second into Excel or into R to get the calculations. All right, so here are the 3 types of random variables we're going to be discussing today. The uniform random variable, the Bernoulli random variable, and a binomial random variable. Now, underneath each one of these, I'm going to outline some brief assumptions that go with each one of these. Now, the uniform random variable has the properties that we can have some arbitrary number of possible outcomes. That is, our sample space could get as big as we like, but the restriction here is that each outcome is equally likely. What I mean by that is that this is going to be very useful for modeling things where anything that could possibly happen, like a coin flip, for example, is equally likely, a head or a tail. If we have a fair coin, that might be an example of how we could use our uniform random variable. These uniform random variables can represent outcomes which are either discrete or continuous. So if I said I was going to pull a number randomly between 0 and 1 from the uniform distribution, that means every possible of the infinite numbers between 0 and 1 are equally likely to be selected. Similarly, I could pull numbers uniformly from the integers from 1 to 10, meaning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, each one is equally likely to be selected. The Bernoulli random variable is a slightly different random variable. This random variable can only take on 2 possible outcomes, and it's going to be useful for us in some particular situations. It's really helpful if we're trying to think about modeling things in terms of a success or a failure. Unlike the uniform random variable, the outcomes here don't need to be equally likely. Lastly, this random variable only models things which are discrete because we're talking about successes and failures. So our outcomes have to be either something occurs or it does not occur. The binomial random variable is related to the Bernoulli random variable in that it is the number of successes of n many independent Bernoulli trials. The outcomes are almost never equally likely, and it's also discrete. Now, the binomial random variable is a way of counting up the number of successes we might observe in a particular number of Bernoulli random trials. So for example, one might ask what the probability is of seeing 5 coins flipped heads when we flip 10 coins, okay? Each coin can be represented by a Bernoulli random variable. It's either heads or tails, a success or a failure. And we're asking about the number of successes, like 5 successes out of 10. So this would be an application of a binomial random variable. To make sure we're all on the right page here, I'm going to throw a set of examples here in front of you, and I'm going to ask you to try and think about which type of random variable would be appropriate for the assumptions of the particular problem we're trying to model here. So let's go through them one at a time. Suppose X here was representing the outcome of a coin toss. Should we be thinking about the characteristics of a coin toss as either uniform, Bernoulli, or binomial? Well, in this case, if we were going to model the outcome of a coin toss, we could think about the probability of a coin landing heads, and it would be fully appropriate to do this either with a Bernoulli random variable, because it either lands as a head or it does not. That's consistent with the success-failure outcome that we would expect for a Bernoulli. But it's also fine for a uniform random variable as long as we have a fair coin, because here there's only 2 outcomes. It's either a head or a tail, and each one is equally likely. Okay, so for the outcome for a coin toss, either a uniform or a Bernoulli random variable would be an appropriate way of modeling that situation. Suppose we were thinking about rolling a die. Let X represent the outcome of rolling a die. Should we be thinking about this in terms of a Bernoulli, a binomial, or a uniform? This one should have a much more straightforward interpretation. There shouldn't be multiple outcomes here because we have 6 possible sides to a die. Each one should be equally likely. That should jump out as a uniform random variable. A Bernoulli can't fit here because there's more than 2 possible outcomes. And a binomial can't fit here because a binomial is again a way of counting up the number of successful outcomes we saw for a Bernoulli random variable. Now consider again whether we're going to have, let's go to another example here. X represents whether or not a salesperson makes a sale. Do we think about this as a uniform, Bernoulli, or binomial? I think a Bernoulli random variable is the most appropriate in this situation because it's going to allow for outcomes that the only 2 possible outcomes here, they make a sale or they do not make a sale, but it doesn't impose additional assumptions that each outcome is equally likely. If we were to suppose this was a uniform random variable, okay, there are still a discrete number of outcomes. They either make a sale or they do not make a sale. However, a uniform random variable is going to impose that there's a 50% chance for each one, and that's not obviously the case when we're dealing with success in sales, for example. Now our last example here says, suppose X represents the number of sales a salesperson makes in 10 attempts. Well, this is a perfect application for a binomial random variable. Okay, we're going to be treating each one of the salesperson's attempts as a Bernoulli random variable. It either occurs or it doesn't. And then we're going to be calculating the probability that they make at least 5 successful sales, or they make at less than 3 sales. This is all about the number we could make out of 10 possible attempts. So here we can see pretty simply, depending on the type of question we're asking here and the type of variable we're modeling, the type of random variable we choose to represent that is going to determine how we're going to calculate the probability for each one of these events. So we're going to go through some examples of how to deal with uniform, how to deal with Bernoulli, and how to deal with binomial random variables. In order to do that, we're going to have to discuss some very simple rules for probability so that we know how to interpret statements that we convert into probability statements. That is how we write an event out so that we can appropriately calculate the probability. So I'm going to write out, there's going to be 4 rules here. They'll be pretty straightforward, and we'll go from there. So let me translate all of the math speak here into English. It's kept this way to be consistent with your textbooks, which I would encourage you to take a look at for this chapter. This is going to be chapter 5 in the text. So this says, let our random variable x be an element of the set S1, S2, and these dots mean up to n many possible outcomes. So here, this says x has to take on one of the possible outcomes, S1, S2, S3, S4, Sn minus 1, up to n possible outcomes. Okay, this is just representing a generic random variable x and some sample space with some events in it. Now, our first rule says the probability that x takes on any value s in our sample space has to be between 0 and 1, okay? Very simply, this just says the probability of an event has to be between 0 and 1. There's nothing that will happen with less than 0% chance, and nothing happens with more than 100% certainty. Our rule for probability statement, our second rule for probability here says if I add up the probability of all of the events in my sample space, it has to sum to 1, okay? Now this is actually a slightly simplified version of this rule, but for what we're going to be dealing with in this class, it's sufficient to say that when we're adding up all of the possible events, we're adding the probability of all the possible events, it's going to have to sum to 1. Our next 2 rules here are going to be helping us try and figure out how to deal with slightly more complicated probability statements. And they're going to help us translate words like and or that we're going to hear many times throughout the rest of this lecture and the rest of this class into a probability statement. So rule 3 says the probability of observing events 1 and 2 is going to be equal to the probability of observing event 1 times the probability of observing event 2. And this will be true as long as our events are independent. Rule 4 says if I want to know the probability of observing event 1 or event 2, then all I need to do is add those probabilities. And this will be true as long as the probability of event 1 and event 2 occurring at the same time is 0. And both of these are going to hold for what we're going to be dealing with in this class, but I'm happy to provide a more detailed explanation at the end of these set of slides that you can look at the more detailed explanations for these 2 rules. Again, the easiest way to think about these rules are if you hear the word and in a probability statement, you need to think multiply. And if you hear the word or in a probability statement, it means you need to add your probabilities together. All right, so let's go through an example here of calculating some basic probability using the uniform random variable and our rules on and or. All right, so here's our simple example. You've got a mechanic that's going to be open from 8 a.m. to 4 p.m. tomorrow. He's got openings every hour, and he's totally unbooked. What are the chances that he schedules you at 3 o'clock p.m.? Now, because we're going to say that they're open every hour with no other possible appointments during those time slots, it's reasonable to assume that each outcome is equally likely. That seems like a great match for our uniform random variable, where we have more than 2 outcomes and every outcome is equally likely. So how we're going to think about this is with these 4 steps. All right, we're first going to define the random variable. That is, we're going to state what our random variable represents. So we're going to say X represents the time of the day for my appointment. We're then going to write the event that we're interested in. The appointment takes place at 3 p.m. We're going to identify the type of random variable, which is in this case, again, a uniform random variable. And then we can just use our simple probability rules to calculate our outcome. So remember that our second rule of probability says when we add up all of the possible events, the probability has to be 1. So let's think about the possible time slots there are. This says the probability that my appointment is at 8 plus the probability my appointment is at 9 plus the probability my appointment is at 10, etc. until 3 p.m. When I add all of those together, it's got to be equal to 1. Now, here's where knowing which type of random variable you're working with is going to make this an easier problem to calculate. Since we are assuming that each event is equally likely, that is the assumption of the uniform distribution, that means that the probability that x is equal to 8 is the same as the probability that x is equal to 9, and that is the same as the probability that x is equal to 3. That is, the probability that I get any time slot is exactly the same, which means I could take this equation that I have here, p of x equals 8 plus p of x equals 9, and substitute in p of x equals 3 for every single one of these events. Since that's the case, that means that p of x equals 3 plus p of x equals 3 plus p of x equals 3, etc., until I run out of events in my sample space has to equal 1. Well, since there's 8 possible time slots, this means 8 times the probability that I get a slot at 3 is equal to 1. So I can rearrange this expression and solve for p of x equals 3. And it would turn out to be pretty obviously, if there's 8 time slots, the probability that I get any one of those time slots is exactly 1/8 or 12.5%. Now, your intuition might have said, obviously 1/8 is going to be the outcome here since there's 8 possible times and each one is equally likely. That's exactly right. I'm just trying to show you how we would use our probability rules to write this expression out more clearly, because there will be some instances where it's not so obvious. And if you can see it in a setting where it is obvious, it may help you in our future problems. Let's take a look at another one here with the uniform random variable. We're going to stick to the same mechanic slot, the same mechanic problem, but we're going to change the slot of possible openings here. They're open from 8 a.m. to 4 p.m., but now we're asking the probability that he schedules you before 11 o'clock. So we're going to do the same 4 steps here. We're going to define our random variable. X is going to be the time of day for my appointment. The event, this is a different event. We're not saying that the event that our appointment takes place at exactly 3 p.m. We're going to say that it is somewhere before 11. If I write this out a little bit more fully, that would be the same as saying my appointment is at 10, or my appointment is at 9, or my appointment is at 8. Again, we're going to use a uniform random variable here, and we're just going to use our same rules to calculate the outcome. Now, rule 4 of our probability statement says anytime I hear the word or, I should be thinking I need to add my probabilities. Now, that means that I can rewrite my probability statement, p of x is less than 11, as p of x is equal to 10, or p of x is equal to 9, or p of x is equal to 8. Again, this is just saying, what's the probability my appointment is at 10, or my probability is at, my appointment is at 9, or my appointment is at 8. Since or means add, this is the same as saying, give me the probability at 10 plus the probability at 9 plus the probability at 8. And as we've just determined, the probability that any one of the time slots is taken is 1/8. So I'm just going to add an 8 plus an 8 plus an 8, and I'm going to get 3 8s. There's a 3 in 8 chance that I end up with an appointment before 11. What we may opt to do here is graphically represent the probability that I get an appointment at any one time. And so to do this, we're just going to plot on the horizontal axis the set of possible events in my sample space. Okay, so here we're going to put this in military time. So we're going to have an 8 o'clock slot, 9, 10, 11, 12, 1 o'clock, 2 o'clock, and 3 o'clock here. To say our random variable x is uniformly distributed, what we're going to do is we're going to represent the probability of any one of these events being selected by the height we observe on our vertical axis. This looks a lot like the histograms that we discussed in our first unit. So this is actually a really helpful tool. It's pretty obvious here when we're dealing with a uniform random variable, but in fact, when you're dealing with any kind of probability problem, it's very useful to try and draw these things out to give yourself a visual sense of the area that you're trying to represent here. So this the middle graph here represents our first practice problem. It said, find the probability that x is equal to 3. That is the likelihood that we have an appointment at exactly 3 o'clock. Well, what we could do here is we could just simply highlight that bar. We would see that there is, and in essence, all we're really going to do here is we're going to calculate the area, okay, of this little bar. Well, the height of this bar is 0.125. The width of this bar, well, this is 1 hour wide. That means the probability that I end up with a slot here at 3 is 12.5%. Lastly, here we're going to be able to graph the same probability distribution function, but we can highlight the event that my appointment is before 11 p.m. by just highlighting 8, 9, and 10. This is a 3-hour gap. Probability of any one of those hours is 0.125. Again, 3 times 0.125, or 3/8, is the probability that I end up there before 11 a.m. So visually here, we can represent these probability statements using these probability distribution functions, or just the histograms, basically, that describe how likely it is we observe any outcome. Now we're going to jump to our Bernoulli and binomial random variables here. Now, our Bernoulli trials and binomial random variables are going to be very closely related. So let me give you an example of the types of questions we might try and answer with these so you can see when the set of assumptions required are going to be met. So we might think about any number of questions in the business world that are related to quantifying the cumulative effect of multiple attempts of some sort of binary outcome. Okay, so let me give you an example of what I mean here. We might ask, how many cars will employees sell this year? The binary outcome would be, on every interaction with a customer, they either make a sale or they do not. Okay, that binary outcome is a Bernoulli random variable. It either happens or it doesn't. And the cumulative effect, the statement about how many would I observe, can be modeled using the binomial distribution. Similarly, I could take a look at this next one and say, how many of our products will be returned this month? Well, either a product is returned by a customer or it is not. That is a Bernoulli random variable. The statement about how many is a probability statement that we're going to think about in terms of a binomial random variable. What are the chances that more passengers show up for a flight than there are seats available? The binary outcome here is a passenger either shows up for their reservation or they do not. Then we're going to ask a question about the cumulative number of people who show up out of the number of tickets that were sold. Last example here, what are the chances that I'll find at least one match in the next 10 job candidates? Well, I have 10 chances for this binary outcome. I either match with a candidate or I do not to occur. Okay, so the relationship between Bernoulli and binomial is, again, binomial random variables are a way of counting up the number of successes we observe for a Bernoulli random variable. So I'm going to give you a very simple example of a Bernoulli random variable here. You're going to think it's quite a derivative example, but you'll see why we're going to use this going forward. So let's focus on a car salesperson that sells a car 25% of the time to a customer. Very simple probability question here. What are the chances that they do not sell a car? Well, let's go through our same steps. I'm going to let X represent whether or not there's a sale. I'm going to define an event. X is going to take on the value no sale. Which type of random variable is this? Well, it's a Bernoulli random variable. Why is it not a uniform? Because sale and no sale are not equally likely. We see that there's only a 25% chance of a successful sale. And now we're just going to use our probability rules to calculate. Okay? Rule 2 says that when I add up the probability of all of the possible events, it has to sum to 1. So the probability that I observe a sale plus the probability I observe no sale has to equal 1. Well, since I know the probability of a sale is 25%, 25% plus the probability of no sale has to equal 1. And just rearranging this expression, I can very quickly see that the probability that my salesperson does not make a sale is 75%. So let's go on to a more sophisticated question here, which is an application of the same sales problem, but we're going to ask a question related to the binomial random variable. A car salesman meets 10 clients each day and successfully sells a car to 25% of them. What are the chances she sells exactly one car today? Okay, so let's be very clear here. When we're saying that she sells a car to 25% of them, what we're saying is that on any one attempt, there is a 25% chance that she sells a car. So if we can make the assumption that these are independent trials, meaning if she's had one bad sale, it doesn't impact the likelihood of her making a next sale. Or if she had a really good day, it doesn't impact the likelihood that she makes sales the next day or not. Then what we're saying is that every single trial is independent of the other. And as long as they're independent, we'll be able to use the binomial random variable here with our basic rules on and or to solve this problem. So let me outline for you how we would model something with a binomial random variable. We're going to let the random variable y represent the number of cars sold in a day. Well, we want to know the probability that she sells exactly one car, so I'm going to define the event y is equal to 1. The type of random variable here is a binomial random variable. And I know this because there is a 25% chance of success on any one of the sales. And there are 10 chances or trials of this Bernoulli random variable, sale or no sale, and we called that variable x before. Please notice I am using a different variable to represent this outcome here, y, and it is related to the underlying Bernoulli random variable x. So we're going to calculate this using our simple application of the rules and or. So hang with me and we're going to talk through exactly how we're going to tackle this problem, okay? Now, suppose she wakes up today, goes into the office, she knows she's got 10 clients that she's going to see today to try and make a sale. We're going to think through all the possible ways she could make exactly one sale among those 10 clients. So suppose she makes the sale on her first attempt. Well, then for us to observe her to only make one sale, that is y is equal to 1, we would observe one sale on the first attempt, x would equal 1 the first time, and then we would observe 9 consecutive fails. Or our Bernoulli random variable would be 0, or represent a failure 9 consecutive times. So I could write this out as x is equal to 1, and then x is equal to 0, and then x is equal to 0, and x is equal to 0, and x is equal to 0, 9 times in a row. Okay, I'm going to show this graphically here to make clear what's happening. In blue, I'm going to mark where I've got a sale, and then I have 9 more fails in a row. Now, how would we calculate the probability of observing this outcome? Remember that from our third rule, that when we hear the word and in a probability statement, it means that we need to multiply the probability of each of the events as long as they are independent. And we are already assuming here that these events are independent, meaning if she makes a successful sale, it doesn't impact whether or not she's likely to succeed the next time. All right, so let's go ahead and calculate this. What's the probability of observing one success on the first attempt and 9 consecutive fails? Well, it would be the probability that x is equal to 1, or the probability that she makes a successful sale, times the probability that she does not make a sale, times the probability she does not make a sale, times the probability she does not make a sale. And that would happen 9 times in a row. So if we group all of the terms, the common terms together, we can see that there is one of these terms representing the probability she actually makes a sale. There are 9 terms where she does not make a sale. And since we know the probability that she makes a sale and the probability she does not make a sale, are 0.25 and 0.75 respectively, we can simply plug in those numbers into our expression here. 25% times 0.75 to the 9th power, or 1.877%. There is a 1.877% chance that tomorrow she walks into the office and her first sale or her first customer buys something and the next 9 do not. Okay? That's one thing we could observe. And there's a 1.877% chance that that occurs. One other possibility, we could see that, or we could observe this next graphic, which is what? It's a sale on the second attempt. So let's calculate the probability that that occurs. What's the probability of one success and it happens on the second attempt? Well, the only thing that's different about this expression is we've moved our probability of seeing a success here from the first spot to the second. And so we're going to group our like terms again. I'm going to have a probability that I don't see a sale right here, probability I do see a sale, and then there's going to be 8 more failures. But again, because we are multiplying these, it doesn't really matter which order these are in. I can simply group like terms again, and I'm going to get 1 sale and 9 fails. This is still the probability of a sale is 25%. There are 9 events where she fails, which happens with probability 0.75. Again, the probability here is 1.877%. So we could observe a sale on the first one and 9 consecutive failures, and there is a 1.877% chance of that. Or we could observe a sale on the second attempt with a first failure and then 8 more failures after that. But here again, remember that the word or actually means add. So if we're going to account for the probability of one sale, we need to keep in mind that it could happen in a variety of different ways. I could get 1 sale exactly if I sold to the first client, or if I sold to the second client only, or if I sold to the third client only, or fourth client only, or fifth, or sixth, or seventh, or eighth, or ninth, or 10th only. But as we've seen, the probability of any one of these occurring is 1.877%, which means that to calculate the probability that I make 1 sale, exactly 1 sale out of 10 attempts, is simply 10, in this case, the number of ways I could possibly make exactly 1 sale out of 10 attempts, times the probability of each one of those individual events occurring. Okay, so this turns out to be 18.77%. That is, before she goes to bed, she says, I'm going to make exactly 1 sale tomorrow. What are the chances that actually happens? If she meets 10 clients, there's an 18.77% chance that actually happens. Now, it turns out this type of problem always has a solution that looks very similar in its calculation to the one we just did. It requires us to know only the number of successes, the number of attempts, and the probability of success in any one of our attempts. These are the big elements of the binomial distribution. Now, if we were to ask the same kind of question about the probability of seeing exactly 2 sales, what we would need to do is find out the number of possible ways she could make 2 sales out of 10 attempts, and then calculate the probability that she would make 2 sales in 10 attempts and multiply those 2 numbers together. Those numbers are going to get a lot busier. And so to give you the intuition for this, I'm going to show you a simple simulation here. And the way we're going to think about simulating this is we've said that our salesperson has a 25% chance of making a successful sale. And so I'm going to draw a number randomly from the uniform distribution between 0 and 1. And if that number is less than 0.25, we're going to credit her with a sale. So here you can see we're on day 2 now. We just drew a number 0.905. That's bigger than 0.25, and so we're going to say she doesn't make a sale. Now, the reason this works out as a representative way for how to model this problem is I'm drawing numbers independently, and the likelihood I get a number that is between 0 and 1 and less than 0.25 is exactly 25%. So it perfectly represents the way her sales behavior would look if it followed all the assumptions of the binomial variable. So we've got 10 clients she could meet with in any one day, and we're going to plot the day on the vertical axis here. At the end of each day, what we're going to do is use a green dot here to plot the number of successful sales that she had, and we're going to watch the first 5 days here. Now, in the gray bars here, what I've done is I've actually shaded for you the calculations for the binomial distribution. That is, if we did that full derivation that we just worked through in the previous problem on making exactly one sale, and were to ask what the height of the bar was right here for the binomial distribution, it would be that 18.77% chance. So each one of these green dots is going to represent the number of successful sales she had on any one day. So if we take a look at this graph, we see that there's one day here she makes 3 sales. Another day she makes 2. Another day she makes 2. Another day she makes 3. And on her 5th day she makes 2. So right here, if we look at this graph, I'll see that there are 3 dots that stack up here for 2 sales and 2 dots that stack up for 3 sales. So this is exactly what this simulation is going to do for us. All right. Now what I'm going to do is I'm going to show you what it would look like in her full year of doing this. Okay, so this is going to go very fast. I'm not going to show you what every single number is that we drew. I'm just going to show you the full simulation. Okay, so we're flying through the days here. And again, what we're going to do is we're just going to plot the number of days on the vertical axis, the client she's working with here on the horizontal axis, and these circles are going to indicate how many successful sales she had on any given day. Now, as I mentioned, the gray bars here are the predictions under the binomial distribution. Each of these green stacked dots shows me what actually happened in our first simulation of her whole calendar year. And you'll notice that these line up very, very closely. In fact, when we talk about, we'll talk about a specific topic here in just a little bit called sampling error. And it's going to turn out that that is the only reason that those circles don't match up perfectly with our bars. So if we were to run this simulation for 1,000 more days or 2,000 more days, it would turn out that the green bar heights would match almost exactly our gray bar heights here. Okay, so I do this not to say that we have to do a simulation like this to show you what's happening, just that the assumptions behind the binomial distribution are reasonable and will generate numbers that we can calculate very quickly. So what I'm going to do here is I'm going to show you how we could actually calculate these in Excel. So to do this, what we're going to need to do is use this function called binom.dist. And binom.dist has 4 arguments. Number underscore s, which is the number of successes we would observe, the number of trials that we have, the probability of success, and an argument called cumulative. Okay? And we'll talk about what that looks like in just a second. Now for our problem, we said we wanted to know the probability of observing 1 successful sale out of 10 trials. We know there's a 25% chance of success on any one trial, and we're going to use the argument false here for cumulative. So what would this look like in Excel? Well, graphically, we've got on the left-hand side, we've got our probability distribution here. This is the same thing that we just simulated, except for the bar heights here, I've got the actual probability calculation. And Excel on the right, you can see how we would actually calculate that. Okay, so you'll notice that if you go through and plug in binom.dist of 1, 10, 0.25, false, you'll get the exact same 18.77 we got when we calculated it manually, event by event by event by event. So this is a great, very simple verification of the way we tackled that previous problem. Now, the argument we didn't talk about yet in this function is what I mean when I say cumulative in the Excel function here. And so let me show you the 2 functions that we could have plugged into Excel using the data from our problem. Okay. On the left is the problem we actually wanted to calculate, which is what is the probability of observing exactly one sail? Okay, here we indicate exactly one sail by using the argument false here in the cumulative argument location. Cumulative means, do you want a specific point in the distribution, or do you want at most that many successful sails? So a way of representing this with an inequality would be to say, what is the probability I see at most one sail? That is, y is less than or equal to 1. That is a statement about a cumulative probability. That is, we are going to add up the probability that she makes one sail or fewer. So 1 or 0. Okay? And the way we would calculate that is binom.dist 1, comma 10, comma 0.25, comma true. And simply, this is just adding up the probability of seeing exactly one sail or exactly 0 sails. Okay, this is what it means to say cumulative. So we have two ways here in Excel of writing probability statements. Now, for the binomial distribution, these are the only two pre-programmed functions that we can use here, which means if we had a statement that said, what is the probability that someone makes at least one sail? That would be greater than or equal to one sail, or any other inequality that is not less than or equal to or exactly equal to. We have to carefully rewrite that probability statement in terms of only equal to or less than or equal to. So to make that clear, I'm going to show you what I mean on the next graph. Suppose I wanted to know the probability of at least one sail, at least one. So we're thinking one or more sails. Well, we can see highlighted here, we can graphically represent that. Well, while it's obvious to see that we could add all of these numbers one at a time, we would have had to have calculated them all separately. So what we're going to do here is we're going to try and figure out a way of rewriting y is greater than or equal to 1 using only the inequality less than or equal to or exactly equal to, okay? Because those are the pre-programmed options we have here in Excel. I could say binom.dist something, something, something true to get less than or equal to, or false to get exactly equal to. But there's no option to get greater than or equal to here. So the way we're going to do this is as follows. We're going to use our second probability rule. Now, our second probability rule says that the probability of all of the events summed together has to be equal to 1. And so what I'm going to do is I'm going to say, well, if I want to know the probability that y is at least 1, this has to be equal to 1 minus the probability y is not at least 1, or y is less than 1. Notice that if I took this term to the other side of the equation, it would hold. It would say y is either less than 1 or it is greater than or equal to 1. And the probability of that is equal to 1. That is our second rule. So what that means is I can write this probability statement, P of y is greater than or equal to 1, as 1 minus the probability y is less than or equal to 0. Okay? Notice here that if I want all of the objects here highlighted in pink, I know that the total probability is 1. So I could take 1 minus the probability of seeing something less than or equal to 0. So in Excel, I would type equals 1 minus binom.dist of 0, comma 10, comma 0.25, comma true. And that occurs 94.37% of the time. What about using things that don't have the word equal to in them? So we might have greater than or less than. Well, we'll have two examples here as well. We could say, what's the probability that she makes strictly more than one sail? That would be 2 or more. Okay, so again, I'm going to encourage you to draw out a little graph here and shade in the areas that you're interested in. Well, we want more than 2, more than 1, so we're going to shade everything 2 or higher. Well, how can we rewrite 2 or more in terms of only less than or equal to or exactly equal to? Well, again, the probability of the whole set of things that could occur is 1. So if we want 2 or more, we could take 1 minus 1 or fewer. That's exactly what this says. This is 1 minus the probability she makes one or less sales. So this is 1 minus binom.dist of 1 comma 10 comma 0.25 comma true. Okay, because less than or equal to 1 is 1 here and true at the end here. That means cumulative. So we're going to subtract 1 and 0, the probability of observing a 1 or a 0 from the total probability, which is 1. Similarly, we could come over here and ask what the probability is that she makes less than one sale. Well, the only way to make less than one sale is if it's strictly less than or equal to 0. Okay, less than or equal to 0. So the way I would write this is I would say binom.dist of 0 out of 10 successful sales with a 25% chance of making a success, comma true. Give me the cumulative probability here. So these possible, different ways of entering probability statements into Excel are the ways we're going to be able to represent different kinds of probability questions and come up with calculations. All of them rely on the same basic information, which is what is the probability of any one success? How many attempts are you making? How many successes are you trying to model? And the rest of it is just identifying which of these situations your problem represents and what you need to plug into Excel to get that outcome. So let's do a couple of very quick examples here to see that we've got this idea under control. So let's go with the following example. A restaurant has booked 20 reservations, but only has 15 tables. And there is a 90% chance that customers will show up for their reservation. What is the probability that they will have empty tables? Now, we're going to want to pause. We're going to want to think through what our random variable is, our probability statements, and write the event out. So before I do that, maybe pause, take a minute, see if you can jot these down on your own. Our random variable here, y, can represent the number of people who actually show up for a reservation. Now, in order for me to have an empty table at my restaurant, it would mean that less than 15 people show up, but I need to write this using less than or equal to, because in order for me to evaluate this in Excel, everything has to be written in terms of a cumulative probability statement where I use less than or equal to, or an exact equality where I would use equal to. So again, this is a binomial random variable. I know that there's a 90% chance of a customer showing up, and there are 20 trials of this Bernoulli random variable. So our calculation here, we don't have to go through the whole step or the simulation. We can just remember that since this is a cumulative statement, we are now just going to ask the probability that y is less than or equal to 14, which is binom.dist of 14 successes out of 20 attempts with a 90% chance of success. And we want it the cumulative probability so that we get less than or equal to. And that turns out to be 1.13%. There's a 1.13% chance that I'll have an empty table at my restaurant. Let's do another one. We've got a student who has decided to guess on a true-false exam that has 40 questions. And we want to know the probability they get at least a C. So to get at least a C, they need to have at least 30 out of 40 questions correct. That would be a 75%. What are the chances that they can guess their way to a C? Well, let's let y represent the number of correct questions guessed. The event to get at least a C means they need at least 30 correct guesses. The type of random variable is still binomial. There's a 50-50 chance on each question. And we know that there are 40 trials. Okay, they have 40 attempts to guess a question correctly. We're just going to do the same arrangement of our problem here. We're going to say that we need at least 30, but Excel can't calculate greater than or equal to directly with the arguments for the cumulative function. It can only calculate less than or equal to or exactly equal to. So we're going to rearrange this expression and say to get something that is at least 30 is the same as 1 minus the probability I get something strictly less than 30, okay? Strictly less than 30, which is the same as the probability of getting something less than or equal to 29. So that means I can calculate the probability of getting at least 30 questions right as 1 minus binom.dist of 29 out of 40 with a 50% chance of correct guessing, and give me the true option, meaning give me the cumulative outcome, and that is a 0.11% chance. There is a 0.11% chance of getting at least a C on a multiple choice 50-50 exam. Excuse me, a multiple choice exam with 40 questions. All right, in our last one here, we're going to take a look at another binomial random variable. Suppose the following: a company is going to let a worker go if they get more than 4 complaints out of 50 customer interactions. If there's a 5% chance of a customer complaint, what is the probability the worker will be fired? Let Y represent the number of customers that complain. The event here to get someone fired means they need more than 4 complaints. The type of random variable is going to be binomial. Since there is a 5% chance of complaint from any one of the independent 50 trials that occur, we can calculate the probability again using the binomial distribution. The probability of getting more than 4 complaints is the same as 1 minus the probability of getting less than or equal to 4 complaints. And again, we have to write it this way so that we can use the cumulative option in our binomial distribution function, binom.dist in Excel. That turns out to be 1 minus binom.dist of 4, 50, 0.05, true, which is a 10.3% chance. There is a 10.3% chance that our worker is going to get fired in 50 customer interactions. Now for your homework assignment for this unit, we're going to be spending some time working with these same kind of binomial, Bernoulli, and discrete probability questions. And to do that, you're going to be working on a sales exercise. So you're going to be dealing with the similar kind of sales exercise we did in our example together. But what you're going to do here is you're going to be thinking about a cell phone sales shop where there are a variety of different workers, all of whom have a different sales style. Some of them spend a lot of time talking to customers, and so they don't see very many customers in a day, but they have a very high chance of closing any one of those sales. There are other people who don't spend so long talking with customers. They turn over customers very quickly, but they have a much lower chance of making any one of those sales. And so what we're going to be thinking about here is how we might use this binomial distribution as a way of making these projections about workers with different types of sales strategies. So this you may work on with one other student. This will be due on next Sunday, July 26th. And you'll have to complete an Excel spreadsheet, attach your work, some figures, and a one-page write-up tackling this worksheet.